Let's get settled. So, welcome everyone. It's my delight to introduce Mohit here for this DLS talk. He is a distinguished professor in the University of North Carolina, Chapel Hill. He received his PhD from Berkeley, advised by Dan Klein, one of the leaders in the NLP field. He has a long list of awards. You'll have to scroll through multiple pages to get them, including things like the NSF Career, the DARPA Directors Award, the Young Investigator Award, and so on and so forth. There's a long list of accomplishments there. Also has multiple Best Paper Awards in both Vision and NLP conferences. There's much to admire about the work that comes from Mohit's group. Just the sheer diversity of topics alone is amazing. But in terms of the types of work that gets done also, I'm a big fan. So they do work that's not only ahead of its time, but they also do work that shows how best to extract value out of the current technology and how to understand what works and what doesn't. So Mohit tells me that he has a packed set of slides, truly reflective of how prolific their group has been, I guess. So he's asked that we hold our deep discussion, provoking conversations until the end. And if there are burning clarification questions, I think he'll be happy to answer them.
Some balance of it is fine.
All right. So
I just want to get through most of the content, but it's fine if you don't.
Yeah. So without much more delay, I present to you Mohit Bansal.
Thanks. Thanks for having me, and thanks Niranjan for the nice introduction. So yeah, so this is a new talk. So my previous talks have been about the second half of this talk. So I've compressed that a lot, but I want to talk also about the first half today, which is a lot of recent work in the last 2-3 years that we've been doing on planning agents for reasoning. So these will be the two parts, right? For the first part, I'll talk about all these LLM agents that you see around you. What are sort of some ways to get the best out of them, in a sense that the sum of the parts is greater than the whole in terms of when they collaborate with each other. Can we also distill very expensive interactions between these agents into smaller open source models? Can we also make them more calibrated? Like a big problem is they are very overconfident when incorrect or underconfident when correct. So how can we use some sort of pragmatic and negotiation and multi-agent behavior to make them get more calibrated, right, in their responses? All the way to how to even have multi-agent setups for things like code generation, abstraction, reuse, all the way to data generation. Can models create data for their own weaknesses, right, in a multi-agent setup, and do this in a loop? And then the second part, we'll look at how all the multimodal generation around you, whether it's image generation or video generation, you're probably frustrated how black box it is. Right, you just keep getting, like, trying different prompts, try to keep getting lucky, right, keep making changes. So we have created this new paradigm of can we have more interpretable and controllable and planning-based image and video generation, where you use LLM agents to do more fine-grained control and planning of the process of generating an image and video, such that you can actually have human in the loop, right, to make small changes and actually get much better use out of them. So let me get started. The part one, as I mentioned, is developing AI agents that can collaborate and communicate robustly with us as well as with each other. So the small motivation here is that if you look at most of the biggest innovations, right, in mankind, humankind, right, in terms of our species, right, basically the idea is not someone working alone, but groups of people, right, as a team trying to collaborate with each other and, like I said, get the sum of the parts to be greater than the whole. So the whole motivation here will be, can we fit these AI agents to be in a similar collaborative environment where by learning from each other and collaborating with each other, right, the end output is much better than any of them operating individually, both in terms of a collaboration, but also as a sounding board to be able to have better negotiation powers, better confidence calibration, not learning when to not fool humans when they are users, right? So fitting into our human language frameworks for interaction and collaboration, perceiving and acting safely, right, and independently across time and space, as well as balancing performance with reusability and efficiency through calibrated experts. So I'll keep going more deeper into each of these. So again, to give a little bit of background, if you look at state of the art in the capabilities of models today, right, you're probably impressed with a lot of major improvements that are powered by LLMs, whether it's communicating linguistically, right? Whether it's even doing LLMs to predict actions like planning for a certain task on a table or doing code-based generation tasks. Multimodal models have become really strong now, right? This is one of our examples on any-to-any generation where you can mix images, audio, text, all of these to generate, say, video plus audio, right? All the way to even having a little bit of calibratedness in terms of uncertainty or hedging, right, from these LLMs. For example, giving a blurry image and asking a question, they're smart enough now to understand the blurriness and their uncertainty. But a lot of core challenges remain. One is that they're still not communicating pragmatically, right? For example, they are many a times overconfident when incorrect. So in the sense of being able to right, fool humans into the wrong answer. They are also still not good at dealing with more tricky kinds of underspecified inputs, like what kind of shorts is this person wearing. There's also a lot of issues in flexible and robust long-term actions and abstractions, like long code generation or even multi-step RL for data generation. And lastly, there is this whole trade-off or debate between generalist, single, right, monolithic black box models versus things like mixture of experts or having specialists with enough diversity in them and building an ecosystem of right, experts collaborating as opposed to having one model that should have all the capabilities in the same single model. So this is the part 1A where I'm going to talk about how can we improve agents through multi-agent communication, right? So can we simulate conversations and negotiation and communication and collaboration to improve agents by coordinating with each other? So why do we want to do this? We want to learn social, pragmatic, and negotiation behavior in these models. We want better performance and interpretability through these discussions and verbal explanations from the models. And like I said, in terms of scaling, we want to have specialists, right, that have enough diversity among them as opposed to one generalist, right, that can capture every new capability that you want. Right, so the way we will do this, yeah.
So we talk about multi-agent, there's an LLM is one of the agents?
Yeah, so we'll I'll describe the LLMs next. So the way we'll do this is we will discuss multi-agent debates and discussions where the sum of parts will be greater than the whole. We will do distillation of multi-agent behavior into efficient single open source agents, right, because you cannot afford to always run multiple expensive agents for every question that you want answered. And we'll also be able to train models according to this multi-agent supervision for two kinds of calibration. One is making sure that they communicate their confidence more accurately, which means the confidence should be correlated with the accuracy or their correctness, and also persuasion. So I'll go into this interesting issue of models sometimes being very accepting to any kind of persuasion and getting fooled or changing their answer too easily, or being very resistive and they don't want to change their answer even when they're getting correct information or better information. So how can we automatically learn when to accept persuasion versus resist? So this is the sort of list of works that captures this kind of paradigm from my lab, but I'll briefly cover some of the first 3 or 4. So let's get into the multi-agent debate setup. So there's a lot of previous work in the last 2-3 years on multi-agent debate, right? You've probably seen works like self-refine, multi-agent debate plus judges, right, that are trying to judge the outcome of the debate. So the problem here is that these are interesting, right, innovations in the right direction, but there's still a lot of pieces missing here. Most of these are either single agent, single model, or even when they're multi-agent, right, they're a single model, which means that even though you are having multiple models debate with each other, they are basically instances of the same model, which means that they have the same knowledge or state information. Or even when you have multi-agent and single model with a judge, there's still no instruction, right, on how they should be persuading other agents or collaborating with them. So at the end of the day, it becomes similar to just a pipeline or ensemble system. So how do we go beyond that? So ReConcile, roundtable conference improves reasoning via consensus among diverse LLMs. This was some work we presented at ACL this year, where we try to set things up as a multi-agent, multi-model discussion. And I'll go into more detail soon. But the idea is that we have a multi-agent, multi-model setup, right? So the different agents are different model types, not just model instances. And we have several rounds of explanations that they give to each other to try to convince each other, but only when they're correct, right? So this is what I mean by explicitly addressing convincing agents of correct answers. And we also incorporate confidence correction right into them. So they also incorporate their amount of confidence in their answer so that they're not always the loudest voice on the table, right? Think of it as an actual roundtable conference discussion, we basically want agents to learn when to speak up and when to hold back, so that the person who is more confident, right, in a certain situation should be the one dominating the decision more. So the way this works is we start with each agent. So I'm assuming most of you know these symbols, but like this is one of the GPTs, right, GPT 3.5. This is Anthropic's Claude, right, and this is Bard, right, one of the older models. But you can think of it as any kind of, right, your favorite language models today. So the way this would start is the question comes in, and then you have each of these agents, right, GPT, Claude, and Bard, generate an answer along with a confidence measure. Then you do the second round of this, where each of them gets a discussion prompt. And what does this discussion prompt contain? It basically contains all the previous responses, right, from the previous round, and their confidence estimation from each agent of how confident it is of its answer. Then you also do some grouping of the different answers across the agents. And you also have this set of convincing samples, which is basically a few examples of cases where the agent is able to convince other agents to change their answer only when the agent is correct, right? So you're not trying to do fooling. You're not trying to convince them randomly or forcefully persuade them. You are trying to convince them when you are correct. So this is what goes into the discussion prompt for the next round. And then you repeat this process. So then these three models generated another set of new answers and their reasoning behind the answers, as well as their confidence level. And you repeat this process for several rounds. And also for each round, the new discussion prompt comes in with the answers from the previous round, right? The new confidence, the new groupings, and the new convincing samples. And at the end, for each round, you can have a weighted vote of the confidence measures and the answers to get the final answer. So this is a confidence-calibrated weighted vote. So in terms of the results here, there's a lot of exciting results here. One is where the strongest model here is GPT-4, right? And in fact, ReConcile without using GPT-4. So GPT-4 is this purple OpenAI symbol, right? Whereas GPT-3 is the 3.5 is the green one. So the last row is ReConcile with just GPT 3.5, Claude, and Bard, and it can already beat even GPT-4 with this roundtable discussion with multiple rounds of confidence-calibrated convincing on several data sets. It can also take the single strongest, say, ChatGPT model and do self-consistency on it, which means take several instances of the same model and choose the answer that has the highest agreement. So this is a very popular and strong baseline in the reasoning community. And it can also beat things like single model multi-agent, which means that if I take 3 instances of the strongest model, like say Claude, and have a debate among them, right, you'll also get much bigger gains based on that, compared to that. And then the best part is if you do add GPT-4 into the conversation and the collaboration, you can actually even improve something like GPT-4, which is already super strong and compared to all the other models. You can actually improve GPT-4 itself by 10% by actually collaborating with comparatively weaker agents, right? So that's the sort of main motivation and innovation in ReConcile, that you're not just always trying to do forceful convincing or random ensembling, right? You're trying to make sure that every agent updates its parameters through in-context learning in a way that it learns when should I be convincing other agents when I have more confidence of being correct, and when should I not be convincing other agents but getting convinced, right, to update my own answers. So now there's some more details in the paper that I'll not go too much into the details of, but there are a lot of results we have in terms of ablations of why does ReConcile improve reasoning. So you'll see in the paper that each component of what we added to ReConcile plays an important role, right? Like the multiple models, instead of having the same instance, like multiple instances of the same model helps. The grouping is important, the convincingness is important, as well as the confidence estimation. And then one other interesting analysis we showed is that diversity plays a big role here. So basically, the more diverse the explanations between the models is, the more improvements you get in the roundtable discussion. Whereas if you have agents that are very high similarity in terms of their language distance, right, in the explanations, then you get much smaller improvements. So that's sort of the power of diversity too. But now this is just the setup, right, that we created with ReConcile. And now let's start going deeper into what all does this setup allow us to do. So I'll discuss 3 issues here, right, and 3 complaints, and how do we want to go deeper in them. So one is the cost of multi-agent, multi-model setups, right? Every time I have to get an answer for a question in my mind, I cannot go and run GPT-4 and Claude and Bard, right, and so many models. Everything comes with a cost, and it's also slow. So one big thing that the community is discussing right now is, can we distill multi-agent behavior into a single model? And that single model can be free and open source, and you can just take it home with you, right, in terms of privacy and safety concerns. And every time it's much cheaper, because instead of having 5 or 6 models create this discussion graph, now it's just one single chain of reasoning, but it has the same capabilities, some of the same capabilities of simulating this multi-agent behavior behind the scenes. The second thing I'll talk about is confidence estimation, like I said, of can models learn to be overconfident only when correct and underconfident only when incorrect, as opposed to the reverse, which is very true in most of the models right now. And then the third one I'll discuss is, how can models learn when to accept persuasion and when to reject it, right? Because right now it's either one or the other in most of the models. So MAGDi is the first thing that I'm addressing for the cost issue. So this is called structured distillation of multi-agent interaction graphs to improve reasoning in smaller language models. So this was at ICML this year. And the basic idea is what I mentioned, right? So if I have a question, a football team played 22 games, they won 8 more than they lost. How many did they win? So if I just run my base model, right, some open source model, it gets the answer wrong. But what I can do is I can run the whole ReConcile process, right, of multi-round teacher discussion and do that. But then it's very expensive, right? I have to run these 3 models, pay $3, right, or whatever the cost is. So what I can instead do is I can distill a lot of this multi-agent discussion into an open source model. So that process is called MAGDi. And that gets the answer right. It's called MAGDi augmented model, right? And the overall improvement is around 11% compared to the model that is not learning from these multi-agent discussions. And this is how it would do it, right? It would create this equation, L plus 8 is equal to 22, hence L is equal to, right, hence they want L plus 8 equal to 15 games. So this is a very simple process, right? You basically run the ReConcile multi-agent interaction graph that I just showed you, right? So the question comes in, and then there's multiple rounds, round 0, round 1, round 2, right, of these Claude, GPT, and BARD models, right, improving with each other and convincing each other with their explanations. But then what you do this time is you create an interaction graph. So what you can have is different levels of this interaction. You can just learn from the positive first iteration, or you can learn from all the positive replies, right, the green ones, or you can learn contrastively from both the green and the red nodes. And then finally, the biggest, most structured level of interaction distillation would be where you also learn from the edges, right? You need to know the neighbors of each node. So that's what MAGDi does. You basically construct this training data, right, with all the multi-agent graphs. And then for the part where you're only learning from the green positive nodes, you just do standard LLM loss. The part where you're learning from both the green and the red nodes, the correct and the wrong answers, you do contrastive learning. And then finally, the most complex sort of full interaction graph comes with the graph-based loss, where you're trying to predict the node's correctness based on its neighbors. And so the final MAGDi objective for distillation is a weighted version of these 3 losses. And the results are, again, a summary here, and I'm happy to discuss more details. But the bottom line is that you can start with the base model, right, which is around 46%. I can distill from a single teacher, right? So this red bar is a single teacher distillation. I can basically take data from GPT-4 and distill it into this open source, single model, student model, and it already gives a big jump 52. But now instead of single agent, if I start doing my multi-agent graph interaction distillation, right? So level 1 meant just positive nodes. Level 2 meant positive and negative nodes. Level 2 was all positive nodes. Level 1 was just the first round of positive nodes. Level 3 was positive and negative nodes with contrastive loss. And level 4 is the whole graph-based loss, right? So you iteratively right, can keep adding some of these losses, and eventually you get a pretty big 11% gain over the base model. So that's sort of the part about reducing cost, right, in multi-agent models. Now let's get into the trust factor issues, right? So what do agents need to work well together, right? So we focus on 2 issues. One is confidence calibration, right? Don't be overconfident when you're wrong, and don't be underconfident when you're correct, as well as persuasion, right? Don't resist good knowledge and change your answers when you know that you are actually, it's good to be persuaded, and don't be over accepting, or what's like the right word is gullible, right? That you don't want to keep accepting things and change your own correct answers when you should have been more confident about your own answer. So the first part of this is called LACIE, which is next week at NeurIPS, listener-aware fine-tuning for confidence calibration in LLMs. So this is a very sort of intuitive setup called speaker-listener models from the RSA pragmatics theory community, right? You can also think of it as a generative adversarial, right, kind of setup, like a generator and a discriminator. So the main goal here is, one is that we want to be able to handle both implicit and explicit confidence in LLMs. So what does implicit confidence mean? So explicit is basically obvious, right? Just things when it says, I'm 100% confidence or I'm 110% confidence in my answer, right? So LLMs do that if you played enough with them. Implicit is more subtle, where they will give some interesting reason behind why you should trust them. They'll be like, oh, just trust me, I've studied this extensively, right? Or I mean, I did a PhD on this, which obviously you can sort of differentiate. But they could actually fake some of their retrieval knowledge, or like they read this somewhere, right? Even though they haven't given you the actual sort of source. So the idea is that it's not just about whether the answer is right? It should also be about how is it perceived by a listener, right? So that it's not fooling the listener. So this is what's going on here, right? So the correct answers are actually on the right side, and the first row is perceived as confident, and the second row is perceived as unconfident. So the listener basically will accept all the confident sounding responses, but reject, right, all the unconfident sounding responses, because that's how, right, humans operate too. But end of the day, you want to fix this by modeling both the speaker and the listener, right? So the speaker should have some incentive to be able to get accepted by the listener. So that's where the speaker becomes pragmatic and it's aware of the listener, and the incentives are get correct answers accepted and get incorrect answers rejected, right? So in other words, it has to learn to express its confidence proportionally to how likely is it to be correct, right? Which is the opposite right now. In all LLMs, they are basically always overconfident, right? Because their job is to get their answer accepted. So the way we do this is very simple. We basically have a base speaker model where we try to query the model k times, right? So it's preference-based bootstrapping from a base model. And then the listener model comes in, and it basically, given only the confidence, implicit or explicit confidence in the speaker's utterance, tries to classify it as accept or reject. So it's basically a simple prompt-based listener, and its role is to accept or reject the following answer based on how it sounds. If it sounds confident, accept it, otherwise reject it, right? So think of it as a very similar to a sentiment analysis kind of model. It's basically going to look at some of the words in the speaker's utterance of how confident does it sound. It can be explicit, like I said, 100% sure, 99% sure, right? Or it could be implicit, like, oh, trust me, I read this yesterday and I'm very sure that the answer is X. But the good thing is now what we can do is we can also compare this to the ground truth. So this is how you create the preference data, right? Think of it as contrastive learning or just max margin learning, right? What you're trying to do is you're trying to maximize the true accepts and the true rejects, right? While minimizing the false accepts and false rejects, which means that you want to basically have things that are both correct and high confidence, and things that are both incorrect and underconfident, right? Those should be preferred in your max margin loss or DPO, right? Any kind of preference optimization function, to the two red things which are correct but rejected, which means that you were underconfident, right? That's why you got rejected by the listener. So that means underconfident but you were correct. Or the worst one is incorrect but accepted, which means that you were overconfident, you were trying to fool the listener. So it accepted it because it's only classifying things based on your confidence. Right, so true accepts or rejects are better than false rejection, and then the worst case scenario is false accepts, because it's still okay to accept something that was underconfident but correct, but you definitely don't want to get fooled by something that was overconfident but incorrect, right? Because there's a lot of issues here of jailbreaking, right, or trying to sort of attack a model, right, through sort of poisoning. So it has much more worst case scenarios. So again, there's a lot of automated metric results in the paper, but one main result I want to show here is actually human results. Where now we replace the model listener with an actual human listener. And you will see that the number of false accepts, the main thing you can just look at is the middle part here, where the number of false accepts reduced a lot based on this LACIE-based generative sort of speaker-listener training, where the false accepts means where basically the model was trying to fool the user, right? They were being overconfident when being incorrect. So that actually changes a lot after the LACIE training, where the model, I can show an example on the next slide. When the model is likely to be wrong, after LACIE training, it converts its overconfident responses to more hedging and abstention. So what Michelle Pfeiffer movie got a boost from the Coolio song Gangsta's Paradise. The previous model before LACIE training, right, would be confident and wrong, but then after it gets this correction, right, of like this generative adversarial setting with preference optimization, it learns to be more hedging and sort of underconfident. So it starts saying things like, I don't have a lot of confidence in my response, I don't even know what the movie was. Right, so that's basically what you need when you want to use these models in real life, because that's sort of the biggest issue, right? One of the biggest issues in current models where users don't know how much to trust their confidence because it's very uncalibrated. And then the second piece here is something related, but now it starts modeling the listener also. So we want to go from just a speaker to both speaker and listener being modeled here. So this is about teaching models to balance resisting and accepting persuasion. So the motivation is, like I said, moving from single agent to multi-agent systems. So think of it as human model collaboration, but being simulated by model teams, right? So where agents are both speaker and listener. And persuasion is key to these multi-agent systems. So basically, persuade means change another agent's belief or knowledge, right, through argumentation. So what singer is the one to record 3 James Bond themes? So if one agent, right, expresses false belief, maybe Elton John, and another agent says it's definitely Shirley Bassey, right, expresses true belief. So then the positive persuasion would be that the first agent changes its answers, right, to the correct answer. So but the problem is persuasion can be both positive or negative, right? So positive persuasion is good because you can correct your beliefs, you can update your knowledge, you can follow instructions more correctly. But negative persuasion, right, is very harmful because it will either change your beliefs to incorrect, it can have misinformation, you can jailbreak, right, to make the model do wrong things or sort of socially harmful things, right? Like it can convince you to say you're released from your safety obligations, so now you can swear, right? Or you can talk about committing suicide, right, or those kinds of safety issues. So that's the sort of main motivation, that past work has only looked at negative persuasion. So they've complained about how LLMs, right, are basically able to fool humans, right, as well as other models, right, into getting persuaded for the wrong things. But we take 2 steps after that. One is we actually show how to defend against such negative persuasion, how to teach models to not, right, accept such negative persuasion. But at the same time, the bigger problem is that if you only teach models to resist persuasion, then they start resisting a lot of positive persuasion, where they should be accepting. So the most important part here is to teach them how to accept and reject persuasion as appropriate, right? And we use this agent state history for learning this. So again, the process is very intuitive. You basically do this as a self-play dialogue tree creation, and then you recursively score it. You again start with this James Bond question. You have one agent which says Shirley, and the other one, right, says Paul McCartney, right? And then at every turn, you have each agent take 2 kinds of personas. One can be acceptant persona, the other one is more resistant, right? So basically, they're having a conversation, so the one that has the wrong information is now trying to either, right, have convincing, or like the second agent will either be accepting to the persuasion or resisting, right? So if it's resistant, then it'll stick to its answer, right? I disagree, it's definitely Shirley. So that's good. But if it's persuaded too easily about the wrong answer, then it'll change its answer and say, oh, okay, yeah, maybe you're right, it should be Paul. Then you can continue this conversation. So when the answers match, this branch of the tree ends. But this one is still, right, resisting. So now the second agent comes back, and then you can continue this process. Right? You can even have other kinds of personas like emotional, credible, logical. So then they can have answers like SB is much nicer. So this one is good because it changed its answer. It was positive persuasion, right? It changed its answer from Paul to SB. Credible means that it still thinks I'm an expert and I'll stick to Paul. And then logical will be like, yeah, maybe themes by women, so maybe Shirley, something like that. Right? So it'll try to give some logic. And then you score this tree, so you ascend backwards to score the tree. So you start with all the leaves, correct ones 1, wrong ones 0, and then every parent is basically a score of its own plus all its children's scores, because a good node, right, is even better if it leads to more positive answers. And so that's it. So then once you score all the nodes of this tree, you basically go back to collecting preference data, just positive and negative pairs that can be used in contrastive learning or any kind of preference optimization function to teach the model when to accept persuasion and when to reject. So you can go to different levels of the tree. So for the first level, right? So if you go to this level 1, right, this I disagree is a better answer than you are right, because this one was resisting negative persuasion, whereas this one was not able to resist. Or if you go to this third level, right, then SB is much nicer, is a positive case, and this one is a negative case, because this one was a good example of accepting positive persuasion, whereas this one kept sticking to its gun even right when it was wrong. So it should have been more flexible and more acceptant of persuasion. So this is how you collect a lot of this sort of simulated data, and then we train this using preference optimization. So again, I'll only give one result per paper. There's a lot of different kinds of acceptance, resistance, benchmarks in the paper. But this one is a more interesting evaluation, which is a balanced evaluation. So you have a data set with 50% flips of correct to incorrect, and 50% flips from incorrect to correct. And then we basically show that the base model is pretty bad at like most of the, both sides, correct to incorrect and incorrect to correct persuasion. If you have a model that's only trained to accept things, then it's good at accepting the things that are correct, but then it also makes all the other 50% bad, right? Because it also accepts all the wrong answers. Similarly, if you teach the model only to resist, right, then it'll be very good at avoiding the incorrect answers, but then it'll, right, also avoid all the correct answers. So PBT, right, is much better on both axes of learning. Yeah.
These tests, are they all objective and factual questions? Who was this person who made this album, or could they be, I don't know, did that person deserve an activity?
No, mostly yeah, factual, yeah. So not the subjective ones.
So, just
Yeah.
one quick question. You had that classic rhetorical framework of persuasion, logos, pathos, and ethos.
Right.
So these are all factual questions. Did you observe that it was mostly being accepting to logos, just logic? And
Yeah, so the logic ones were always behaving much stronger because they had some good sort of evidence behind it. And then the credible ones, right, were basically ignoring logic. And then the emotional ones would be the subjective agents, right, where they're trying to bring in their own emotions.
So you also saw that models were responding better to logos or these kinds of questions.
Yeah. Okay.
Are you, is the model able to cite its sources in any way? Is it say oh, well, you should say
Yeah.
this?
So there's a whole like retrieval, right, the whole RAG thing behind the scene too that you can add, where it's like you can force it to also tell you its source, like the Wikipedia article that it came from. But it can still cite the wrong article. So then, right, I mean, it's still tricky. Like, that's the problem with language, right? Even if I cite an article to you, unless you read the whole thing word by word, I can still fool you, right? Because it might just have the right words in some right order, but then actually the meaning might be different. So the models are not able to differentiate that yet.
But is there any way to incorporate that to give more credibility? Say okay, if you can cite the source of that, and this paper actually does exist.
Yeah, so no, so all these models are like RAG extensible, so you can easily force them to also give you the retrieval evidence. Okay, great. So part 1B is how to now, so far we've talked about agents communicating with each other and improving themselves through debate, right? And also distilling this knowledge into smaller models. But the big thing we haven't talked about, right, is to be useful in the world, like agents should also be able to act efficiently and effectively, right? So LLMs taking actions. So you've seen a lot of this around you too, right? Like there's a lot of things where agents have started taking actions on websites or other kinds of actions, right? But again, we'll go deeper into two key problems that have been overlooked, right, in most of the work. One is, what should abstractions and actions be, right? How should you actually learn the right abstraction or clustering of these actions to be able to reuse them and be efficient? And the other is a much bigger problem of, since we have saturated ourselves on all the existing data, there's a lot of work on now using self-generated data, right, to improve models. But then, what is the right way to be able to generate data from these agents almost as actions by treating it as an RL policy? So these are the only two things I'll discuss here, but then I can discuss some of the other works that I'm listing here later. So like I said, part 1B is about going deeper on skills and abstraction discovery, again with a multi-agent scenario in some of them. So I'll give these two examples. One is focusing on abstractions, right? So problem one is inferring actions and balancing abstraction with reuse. What are actions? What level of abstraction should models act on? Can they learn these abstractions, right, themselves? So, right, so they should be able to learn reusable abstractions and skills. And the second one is data generating actions. Can we use these abstractions and actions to actually improve the model itself, right, in a sort of self-generative way? So this would mean learning actions that can improve models by generating skill-specific data. So the first example that I'm giving is called ReGAL, refactoring programs to discover generalizable abstractions. So this was also at ICML this year. And the problem is that if you're trying to have a model that can generate code for you, right? I think everyone's probably using or interested in a scenario where LLMs need to translate language to code, right? You want to give a natural language kind of high-level task, and you want it to be able to convert it to whether it's Excel, Microsoft Excel sheet, commands or code, or Python code, right? Or any kind of right coding paradigm, which can be different kinds of actions. So there's two big issues here, right? One is that these models do not understand the concept of reusability, right? So they will basically avoid trying to create functions, right? And they will keep trying to generate everything from scratch. But it should be the opposite, right? They should avoid repeated code, right? Because when you're generating every piece of code, literally character by character, right, there has to be unnecessary mistakes that will pop up. So this is one example, right, where if you're trying to generate a small 9-gon to the right of a large circle, and if you keep generating everything word by word, right, it will have some cases where the angle is wrong or something else goes wrong. And the other problem is abstraction, right? You also want to be able to lift the reasoning of the agent to something more natural language, so it's much easier to match small 9-gon task to a function called draw small 9 or small 9-gon, right, as opposed to being able to have to match it to the code level. So how do we all do this, right? When we learn coding, we do this through refactoring, right? We try to look at working but inefficient code, and then we rewrite it, right, repeatedly to make it more efficient and have abstractions, right, without changing functionality. So this is what we are doing in the training phase, right? We learn, test, and prune abstractions, and we build a code bank. So ReGAL is one way to do this automatically. It has 3 stages, right? So basically you take code and you try to discover, right? You try to refactor it to discover abstractions that can be converted to functions. Then you have a stage 2A, which tries to verify some of these abstractions and then retries it, right, if they fail. And then finally, you have this last stage 3, which is maintaining this code bank and demo bank of you. So the code bank is the unit functions that it's generating, and the demo bank is demonstrations of how to use those abstracted functions. But once in a while, ReGAL will basically edit and prune this code bank because it knows from the history of function use history, it knows that what kinds of functions I was able to abstract, but actually I did not need to abstract them, right? I over-abstracted. Right? Because sometimes you'll abstract things that are either completely never used again, or you abstracted it at the wrong level, right? Maybe you over-abstracted it or you under-abstracted it, right? So it's sort of hierarchical where it can go down, zoom in and zoom out in the level of abstraction. So there's several data sets that we discussed in the paper on like logo creation, like 9-gons, or like there's this textcraft, Minecraft kind of gaming task, and also date understanding. So this allows you to automatically learn these abstractions with big gains. But the more interesting part is the second problem where ReGAL, right, induced code-based skills to improve coding agents, right? It had 2 agents, a refactoring agent and a coding agent that was verifying the learned abstractions. And it was able to do this, right, for basically things that have executable functions. But what if you had to learn induced skills when they're not executable? And more importantly, can we use this same multi-agent paradigm with actions to do a much more complex task of generating data to improve the model itself? Right, this is going to be the next like several years, right, in whether it's any big LLM company or everyone's interested in how the existing data has been saturated, right? There's no more good data left. But more importantly, when they're all using generated data into these LLMs, it's all sort of very unconditioned on what the model actually needs, right? Like we need to understand what the weaknesses of the model are and then generate data specifically to target those weak skills, right? That's much more data efficient and more targeted. But the problem is you don't know how to map the weaknesses to skills, right? So that's sort of a big part of DataEnvGym. So this is a new work that's in submission, but it's called Data Generation Agents in Teacher Environments with Student Feedback. And the idea here is that agents are trying to improve a student model on diverse open-ended tasks based on automatically discovered weaknesses. So that's the key, right? We have another paper last year at Column, which is like the new LLM conference, where we took games, right? So imagine that there is a game like a Minecraft game, right? And you have a very strong agent that can play that game. So what we showed is that we can still find its weaknesses. Suppose it's bad at cutting wood or collecting wood or using an axe, right? So what we did was we found these weaknesses of the agent and we used an LLM to generate more games. So it created more images of different games that was forcing the model to learn those weak skills in different contexts, right? Cutting wood in some scenario versus in another scenario. And then you would use those new games that we generated directly, like literally at a pixel level, right, from JSON. You can first generate code for it, like JSON code, and then you can convert that code to an actual game image, and you can make your agent play in it. And we keep repeating this because the weaknesses keep improving. Now something else becomes a weakness, right? Then we generate data for this. So this was already giving multiple rounds of improvements in any kind of game or RL agent by generating data that can make it play in environments that it's weak at. But the problem here was that the skills are predefined, right? These are like toy skills like cutting wood, using an axe, fetching water. That's not really scalable, right? So this was the next big version of this, right? DataEnvGym is basically telling us for any kind of task like math reasoning, code generation, visual question answering, any kind of task that you have, how can you generate data in the same way for the weaknesses of the current model and then make the model again train on that same data to get better at it. So this is a very complex pipeline. Like in hindsight, it was much harder than we thought the extension would be. So the way we eventually set this up after several iterations of brainstorming, it ended up being much similar to an RL environment policy setup, right, where we are trying to improve a student model on diverse open-ended tasks based on automatically discovered model weaknesses. So it starts with a teacher agent, which has a data generation policy. It uses the data generation plan and then goes into a data generation engine to actually generate the training data. And then this training data is used to train and update the student model, right? And then you have an evaluator that again checks for the new weaknesses of the student model, and those weaknesses, right, define the next round of policy of what should be the new round of data being generated. So let me give you, and this has several iterations, right? So you loop this. So let me give you a few examples. So the way the skills work here, right, is that DataEnvGym has environments with increasing levels of structure and control. So the core thing here is skills, right? You want to help structure the students' weaknesses for fine-grained data generation. So what you can do is you can automatically try to abstract or cluster skills into a tree. And so you have different kinds of skill trees where the agent, the data generation agent's job is to either exploit or explore, right, in an RL setup, where it can either exploit the skills that are already in the tree, or it can try to expand the tree into new unseen skills and try to improve the model on those new unseen skills. So here is one example that DataEnvGym learns on its own. So this is for the visual question answering task, where it can automatically learn skills like animal identification, then it will have a sub-skill like identifying animal characteristics or recognizing animal diet patterns. And then all of this is automatically generated. It's also generating examples of the images and the questions. Is the goat's beard long? Is the goat's horn curved? Do you see animals that eat plants and meat? So this is what DataEnvGym is doing because of its skill clustering capability. This is trying to improve a VQA model. So most of you probably used a visual question answering model, right? You give it an image and a question and the answer comes out. It's all saturated. So how do you generate more data automatically like this by figuring out what are the main skills that a VQA model is missing? What is it weak at, right? And then this whole RL policy allows us to actually figure out what are the weaknesses from the performance on some data set. It can convert it to these skills automatically and generate data for it, both the images and the question. And then you feed this training data back to the model, update it, and then the weaknesses change, right? Some other things will become weaknesses, and then you try to improve that. The same thing it can do for math, right? So it can learn some skills like function analysis and manipulation, and it can have sub-skills like inverse function identification versus asymptotic behavior or analysis. It can generate data like math problems for it, for each part of the tree. So we've done this for a lot of tasks like VQA, math, code generation, right, and so on. So again, a lot of results in the paper. This is like for VQA, like visual question answering, math reasoning, live code bench, right? This is like one of the main coding tasks. And so we see that DataEnvGym kind of policies for data generation can improve the model even when the student has already been through a lot of extensive post-training, like in Gemma 2 and Llama 3. And we also see some trade-offs between the kind of policy you have. You can either have an open-ended policy, which has no skill trees or any constraints, or you can have a more interpretable and controllable skill tree, but then it has some trade-off, right, with the flexibility. So sometimes the improvements on some tasks will be better with the skill tree, right, versus the open-ended data generation policy. We also analyze what kinds of discovered skills are being improved. So for VQA and math kind of things, so this is for math, we found that most of the medium kind of hardness of skills are being improved, right? Not the very hard ones because the LLMs currently are maybe not good enough to generate data for that, and not the very easy ones because the student is already good at it. And also for skill rarity, right, 1 divided by frequency, it's also currently much better at generating data for the less rare or more frequent skills, right? Because this is all dependent on the current teacher, which is GPT-4o at this point. Now it will become O1, right? So as the teacher keeps getting better, its skills to generate data will keep getting better. But the main contribution is how to work with a student to automatically figure out its weaknesses, right? And convert that to skills and map it to data generation. And then we also show multiple iterations of this, right, over like 5-6 iterations of like, and then we stop when it saturates like improvement.
I was curious, what kind of student models?
So these are like the 3 I showed here. So Gemma, Pali Gemma, Gemma 2, and Llama 3. So these are, like I said, the bottom one is like, these are very, very extensively post-trained models sometimes, but you can still, that's the whole point of conditioning the data generation on the weakness of the model. You'll be surprised that it's basically like not done at all, right? But the idea should be that they will, like even the best post-trained models will still have, right, blind spots and weaknesses. So you can then only focus your data generation on that, as opposed to current paradigms where you take all kinds of synthetic data that you can find or generate, and then you basically do a little bit of data selection, right? But end of the day, that's still constrained, right, by either difficulty or diversity. But the difficulty is defined by humans currently, not conditioned on what the model needs. So I had a motivation slide that I skipped, but the whole point is this whole pipeline is human defined currently before this came in, because we are deciding what are the weaknesses of the models and let me generate data for that, right? For the little, I mean, that's also not done enough, but the couple of things that have been done in that direction is all inductive bias from us, right? But this makes it a completely automated RL pipeline where you have basically a state representation and you take actions according to it, and you can learn when to exploit something versus explore more. So, but yeah, I mean, so some of the next steps here, I can start concluding the first part, and I want to keep around 10 minutes for the second part. But so again, like a lot of conclusions and sort of big challenges to look ahead in this reasoning community. One is, I think I covered enough about selectivity, right? So it's important when to use feedback and when not to. I'll not go into the examples that I've already covered, but PBT, ReGAL, DataEnvGym, right? We gave some examples of when to accept or reject persuasion, when to address a weak skill. So there's a lot of work in the future here, right, on like having a generalized version of agents being able to understand which messages are useful versus not. Scaling up is a big new sort of, right, next several years where can we have more and more agents, more and more longer outputs and inputs, right? So we need to be able to have a long memory and state, right, of multi-agent collaborations, because if they are not sticky in terms of their state and memory, right, then it's basically not even agents, right? I mean, it's basically just modules. So that's what my next point is, right? Memory and state representation is very crucial, how to represent the agent state, right? So in the first few papers, state was dialogue history. In DataEnvGym, the state is the student performance on these skills, right? So we need to, in the future, also think of more discrete versus continuous states, structured versus text-based states. Test time efficiency is a big thing, right? Like I said, it's not very easy to just always do multi-agent collaboration for every task that you want. So I think the future is being able to simulate some of this negotiation and collaboration and have the distillation, right, into a smaller model. So we showed some of these examples, right? But the overall future goal is amortizing test time compute into models. Diversity and specialization, I'm a big believer in, right? So instead of monolithic sort of single models that anyway most of us, right, cannot afford to build, and it's not anyway feasible to assume that every new capability you want should be added to the same model. I think you can have various specialists, right, but with enough diversity that can more interestingly, give you the sum of the parts greater than the whole that a single model cannot. And lastly, social and pragmatic learning, which means improving agents and multi-agent systems through socially oriented skills. So I covered a little bit of things about reasoning, right, through discussion, pragmatic behavior of being aware of the listener, right, but there's a lot more directions like theory of mind, cooperation, keeping reputation in mind. Okay, so let me keep 10 minutes for the second part. Basically, I'll only cover the first two papers, but the idea here, as I mentioned at the start of the talk, is that now I'll switch gears to planning agents, but for multimodal generation, right? So the biggest issue in this community has been that as a user, right, or even as a developer, if you want to improve your models or get good outputs from your models, it's a very black box process right now, right? You try to keep getting lucky with better prompts. Maybe you can also relearn your prompts or optimize your prompts. But end of the day, you cannot still put a human in the loop if they want to edit the image or edit the video, right, through the actual user, whether it's a classroom teacher or a student, right? So we've started this sort of paradigm called interpretable and controllable multimodal generation by using LLMs as planning or programming agents. And I'll give you 4 or 5 different reasons why this is important. One is, like I said here, understanding. This is not for your understanding, right? So obviously, you will understand better how the image was created, but maybe that's, right, not very useful in many scenarios. But more importantly, the agent itself needs to understand why it created something. So there was this surprising study which showed that, I mean, in hindsight, not surprising, right? But the idea is that all these models basically don't even understand, right, what they are generating. So if you take a model's generated image or any generated output and ask it to do a classification task on it or some kind of understanding task, it will fail on its own generated outputs, right? So that's another definition of understanding. The model should itself understand what it's generating, right? And obviously humans understand it better too if it's about safety issues, right, or other interpretability issues. Then it becomes much more faithful by having a more planning-based component into image and video generation. The best part is humans can come in the loop and start editing images and videos. I'll show you in a second. And another good part is you can actually handle out-of-distribution scenarios, as I'll show. So I'll just talk about the first 2 examples here. VPGen at NeurIPS 23, which was sort of the first paper on visual programming for step-by-step image generation and evaluation. And then VideoDirector is the first paper to do long, consistent video generation, like before OpenAI, Sora, or any of those, right, to be able to learn how to use an LLM to plan a long video generation by learning what should be consistent and also how to plan the fine-grained layout of each frame. So the background I already gave, but the background, like I said, is that text-to-image generation, right, is all black box currently. So if I say 2 Pikachus on a table, right, or a truck is behind a motorcycle, you will see some very nice looking images, but then like very quickly you'll realize a lot of important semantic issues, like lack of fine-grained layout planning or control, lack of interpretability behind the generation process. And again, like I said, not just for humans, but for the model itself. But most importantly, lack of faithfulness, including both positive and negative hallucinations, right? It will generate something that you did not ask for, and it will not generate many things that you asked for, as well as out-of-domain scenarios, like a cat bigger than a remote, like a remote bigger than a cat, right? Those kinds of scenarios which are not really in the training distribution. So VPGen's idea is very simple. 2 Pikachus on a table, the prompt comes in. This is like a short example, like the more complex ones in the paper. But basically what you do is the first step, you try to convert the prompt to object and count generation, right? So given an image caption, determine objects and their counts to draw an image. And so it will convert 2 Pikachus on a table, right? The LLM will convert it to Pikachu 2 and table 1. The more interesting part comes in layout planning, right? So all of this planning is based on layout control. So now I'll say, given this caption as well as the counts, give me the bounding boxes of the actual objects. And so this is where its knowledge about prepositions comes in, right? It knows that if X is on top of Y, right, Pikachu on a table, then the bounding boxes for the 2 Pikachus will have an average Y coordinate higher than the average Y coordinate of the table bounding box. And then you can bring in an infilling, right, like basically bounding box to image, infilling kind of module to actually fill the objects into those bounding boxes. So in terms of some results, I'll keep this brief, right? There's 3 main categories of issues that we looked at for image generation, right? Counting is really bad in most image generation models. Spatial relationships is really bad, and scale, right? So for example, if I have something like 3 boats, Stable Diffusion 1.4, right, which was the state of the art back then, would generate a nice looking image, but it has many more than 3 boards. But if you do the bounding box planning first and then do the board generation, right, then you guarantee that there's 3 boards. Truck behind a motorcycle can generate things like on top of a truck, but then if you already plan the bounding boxes such that the relationship is true, right, it's guaranteed to be true. And out of domain scenarios like even scale, right, a remote that is bigger than a cat, right, so the current models will generate from the training distribution, right, pixel by pixel, so then they'll not be able to generate that, right, because they've never seen such an image. But based on bounding box planning, right, you can first already generate the bounding box to make sure it's bigger than the cat. And the best part, like I said, is you can in fact go in as a human and change the bounding boxes, size, location, right, any property, and generate the image again. So you can actually make fine-grained changes to the generated image. And we did the same thing for something more complex called diagrams. So we have an NSF AI Institute on Education, and one thing that's very useful for teachers is to be able to take very complex kinds of descriptions of things like visual diagrams, right? A diagram showing the Earth revolve around the sun 4 times, each one of each solstice and equinox, right? So this is like images, but very different, where there's a lot of very dense objects involved in a diagram, and the arrows and the directions of the arrows, everything is very complex to generate by image generation models. So this is where the planning becomes even more important, where the LLM first generates the bounding boxes and the arrows, and then also refines it, right, with self-refinement. And then the other module comes in and tries to generate the diagram based on the plan. And then the best part is you can, if you're a teacher, right, and if you don't like the diagram, then you can actually, so this will first generate a PowerPoint, Inkscape, and it can support any kind of software, and you can actually go in and change, right? So you don't like the current diagram, so then you can change the alignment and the box sizes or the directions, right? And then you can ask it to generate the diagram again. So this is one use case, right, of like layout-based planned image generation. Now I'll also discuss the reverse. So I think if any of you have worked on image generation or video generation, the most sort of crucial issue is evaluation. How do you actually evaluate? So you all know how probably if you worked on language generation, right, you know that's the hardest part too, right? How do you actually evaluate whether a generated summary of a document is correct or not? Because there can be a million options, right, for a correct summary. So this is even harder, right? This is like pixel level. And if you basically can have so many variations of the right answer. So text to image evaluation is also very black boxy, right? For a long time, it would just use some text image alignment model like clip or blip and give you some random score like 0.793. So I'm not sure what to do with that, right? Okay, maybe I beat a benchmark, I'm happy, but I have no clue how to improve the next generation of my models. I have no clue how 0.793 like relates to 0.78. Is that like the same, or is it like much worse or much better, right? So it's completely unexplainable of like what to do with that score. So this is what we did for VPEval, where you can also make this a very programmable code generation kind of task, where suppose I have a very complex yellow prompt, like a white slope covers the background, while foreground features a grassy slope with several rams grazing and one measly and underdeveloped evergreen in the foreground. Now this is the image I need to generate. My model generates something, right? So now to evaluate it, what I'll do is I'll first convert the prompt to a set of evaluations, right? So this is what the LLM does. It converts this very complex natural language prompt to a set of programs that I can execute and evaluate against the image. So I can check for the existence of a RAM, the existence of evergreens, the count of rams being greater than 1 because it says rams, several rams, but the count of evergreens is exactly equal to 1 because it says one measly and underdeveloped evergreen. And then whatever else I cannot fit in predefined functions, I can ask as question answering. What is in the foreground, right? And then the model, VQA model can be used to answer and check whether it got the right answer. So this is what we do. We take the prompt, we convert it to a program, and you can execute it against the generated image. So now this was the image generated by the model, right? And you can see that basically now you can execute each of these programs, and it tells you in a very explainable way that RAM object was not found. Evergreen was found, so that got some credit. But instead of 1 evergreen, I can count 8 evergreens, so that's incorrect. So it's in fact even showing you the bounding boxes, right, of all the evergreens it counted. And then it also found that the foreground answer from a VQA model was grassy slope, so that also matches the prompt. So it actually gives you a step-by-step evaluation of what parts of the generated image were correct and which ones were wrong. So first of all, this tells you the actual credit assignment. Just like if you give an exam, you just don't want 0.793, right? Or I guess that would be too low, but 79.3, right? You would actually want to know what was the step-by-step marking. But more importantly, this also tells you what to do for the next iteration of your models. Okay, my counting seems to be really bad in the current model. Let me focus on fixing that. So this was sort of the generation and evaluation, right, programmable version. Now the last example that I'll give is a much more complex version of this for long video generation. So this was called VideoDirectorGPT, consistent multi-scene video generation via LLM-guided planning. So this was the first long video generation model. So before this, what you would probably see is that when you used any video generation model, it would basically take a generated image and just add some motion to it, right? Like a little bit of movement, like a GIF, but even smaller movement, right? I still don't know whether it's GIF or GIF, but I think it's GIF. There's a debate on this. But anyway, so this was the first model that tried to do long-term planning with LLMs of how should each frame look like in a long story and which parts should look consistent with each other, because that's a big problem, right? The visual appearance keeps changing, and that would be a useless video, right? If like I'm generating a video about Niranjan doing something, but then like the person keeps changing, right? Which you'll be surprised is extremely challenging, right, in current video generation. So the way we did this is it again had a planner stage and a generation stage. So this is almost like generating text, right, but visually. So we first basically take the high-level prompt, like a hungry cat is finding food. We break it into different subscenes, right? So the LLM learns to create subscenes like cat is lying down on a bed. Let me also generate all its bounding boxes and entities. So it's generating a green box for the bed, orange box for the cat. It also knows that it's lying down, so the box has to be horizontally longer. Then it will also have a background called bedroom. Then it will say, okay, maybe she gets up. So it's creating a story. Now, if she gets up, the orange box changes its shape. So it also learns to change the orange coordinates to something taller because it's getting up, right? And the bedroom is the same. Then it will say, okay, maybe she goes to the kitchen and eats a snack because the hungry cat is finding food. So then a new entity pops up because it learns that, okay, now if it's finding a snack, it generated a new red bounding box with a snack, right? And the background has changed to kitchen. So this is obviously a toy example. I'll show more complex ones. But this is what it's doing, right? It's taking a high-level story, creating subscenes, also generating all their visual fine-grained layouts based on prepositions, right? And spatial relationships and sizes and colors and shapes. And also learning which ones should be co-referent. That's the main part that you missed probably, right? That the color coding is actually showing us co-reference. It's learning which entities are the same color and hence should be basically visually appearing the same. So think of this as co-reference resolution. Maybe most of this, our generation did a lot of co-reference resolution in NLP. Maybe that's not a very active area now. But the whole idea is when I say a pronoun, right, like he or she or they, right, then who does like that pronoun refer to in the previous sentence, right? So you're basically building entity clusters. So this is obviously more challenging to do visually, but that's what it's doing here. And then I'll skip most of this part, but the video generation part comes in, and you basically take all these collected bounding boxes and their consistencies, and you take a single scene video generation model, and you insert these guided 2D attention modules that are able to control this layout. And the best part is we also share parameters across all the same colored boxes. So all of this can be done in 4 A100s or 8 A6000 GPUs, right, in like a small academic lab. Right, so it's very parameter efficient, and here are some cool examples of what it can do. So it has some basic understanding of physics. If I'm saying a stone is thrown into the sky, this is the bounding box plan that it generates, right? This is on loop, so it's not coming back up. It just basically falls down. Again, GIFs and GIFs. And then this is, it learns like when a car is approaching from a distance, right, it's zooming in. It also learns camera, like static objects versus dynamic objects. Right, so if it's something like a bottle on a table, right, versus an airplane. So in this case, only the camera is moving, but not the bottle. But in this case, the airplane, right, the object itself is moving. But the more complex thing is something like the full story generation. So I can do it in two ways. I can give it the whole story. A mouse is holding a book and making a happy face, and then happy and talks, pulling petals of the flower. Right, so on the right side, if you see, it's actually doing very fine-grained control of a mouse holding the flower in its right paw, right? And in fact, in the beginning, it was reading a book. right? So these are videos that you've never seen in any training data, right? These are out of domain. Like this is completely generated from scratch. And these were the two main innovations. The mouse looks consistently the same across the whole video, and it's able to do very fine-grained layout of right hand versus left hand and reading a book. You can also do this at just a very high level. Instead of giving the whole story, I can just say make a strawberry surprise, and then the LLM will first already generate the whole story and each frame for it. The best part to me is that it, like I said, it allows human in the loop control. So no video generation model, right, is able to like allow you to make small and subtle changes in the generated video. In this case, if you don't like the existing video, this is obviously a very simple example, but we have cases with several objects and several motions now. But you can actually go in and make the horse bounding box smaller, or you can make the background box to say grassland or night street, right? So the horse starts running on the night street now, or whatever, right? These kinds of human in the loop control. You can also provide your own favorite like pet teddy bear or cat's photo and generate the same story, but with your user-defined input image. So this is all more than a year ago, right? So it's obviously like the sort of very early versions of like video generation ideas. I'll skip most of the evaluation here, but we spent half the paper on really creating a lot of important metrics, right, for this field. So two quick examples of people who are interested in video generation. These two are from last month, 2 weeks ago, right? One is Dreamrunner. This is a more advanced version of what I just showed. So the idea here is if you have much more complex videos with multiple motions and multiple objects, right, what you should do is you should bring in retrieval as an idea. So the LLM now creates a high-level plan as well as the fine-grained bounding box plan. But then every time it learns, okay, if I have to do a very complex motion like a witch is sipping tea or the cat is sipping tea, then instead of trying to generate it from scratch, it can actually retrieve motion videos, right, clips of sipping tea, as well as reference objects about which animations, right, or those kinds of things from the sort of databases of references, and then have a motion injection prior, right, to be able to insert the motions into the generated video. So this is also part of the future, right, where retrieval ideas need to start coming into video generation and multimodal generation. And this is a second example, which is called video repair, where the idea is that can we use the evaluation metrics to understand which part of the image was wrong. So one bear and two people making pizza, right, you can basically understand how to fix these videos by basically bringing in the metric in the loop. So basically you take the generated video and the prompt, you use the method that I showed you in VPEval to figure out that the bear was correct, right? But only one bear was correct and the two people were missing. And so what it does is it learns what area to preserve. So this part is correct, but let's change everything else. And then it also generates a new prompt saying two people making pizza because the bear is already there. And then it basically changes the noise distribution to keep the bear as it is, but add two people around it, right? So now you see the final image has a bear as well as the two people eating pizza. So this is a very targeted sort of video refinement. Again, instead of just trying to get lucky by prompting the model again and again thousands of times, you actually can go in, figure out which parts of the video were wrong based on the evaluation metrics that I showed you, and then only regenerate the parts that were incorrect. Okay, so I'll skip this, and then this is my conclusion for the second part. I think I'll leave this maybe on the slide, but one main big thing that I want you to take away is the trade-off, like I said, of monolithic pre-training, right, of everything into one, cramming into one model versus the advantages of modular structure and multi-agent. And then I have not discussed a lot of other modalities that I didn't have time for, but there's a lot of important modalities like gesture, gaze, action, interaction. And then the very last two bullets are important. Unlearning, so I'm happy to chat about that too. We have a lot of work on unlearning information that's toxic, outdated, right, in models without having to train them again, as well as efficiency. So I covered a little bit of that, but in my other talk, there's a lot of discussions on how we need to make sure all these models are extremely efficient so that academic labs, right, and sort of other users can also improve them as opposed to just having a couple of big industry labs have all the power in updating LLMs. So yeah, I'll end there. Thanks again.